Now let's see what are the geometric characteristics of the structure that are usually calculated by the designer. So this is going to be a quick revision of the notions that you have been studying in the basic school physics. So for example, because basically a designer of aircraft is going to be calculating the surface area, for example, the body volume, and moments of inertia and some other things that you basically know, but you have to understand well in order to understand aircraft design in the subsequent courses and in the subsequent years in study on the aviation university. So we can start, for example, with the basic things that is calculated all the time by aircraft designers, which is the surface area, which is basically numerical characteristics of a two-dimensional, either flat or curved geometric figure, showing informally its size. So, for example, an aircraft designer will talk about the surface area of the wing, which defines how much lift can be generated and also how much drag, right? We can, in structure, we talk a lot about the surface, the cross-sectional area of structural elements, which also determines how much load can be taken by each and every element of the structure. So it is a very common and very important notion that is going to be calculated all the time by aircraft designers. And some other notions include, for example, the static moments of an area, which is the area itself multiplied by a certain distance towards until an axis. Right. So this is also a general notion that can be also used sometimes in aircraft design. The center of mass, which is very important thing in aircraft design, and there's an entire process that is dedicated to finding the proper location of the center of mass of the aircraft. And why it is so important? Because it will say everything about its controllability and its maneuverability and its stability in the air, right? So, for example, moving something inside of the aircraft, some system, some equipment, fuel, loading engines, and so on, payload inside of the fuselage is going to shift its location of the center of mass, and the center of mass is being calculated all the time using these, for example, equations, where the coordinates, for example, the x-coordinates of the center of mass is calculated as sum of all of those masses multiplied by their coordinates and divided by the entire weight of the system, which is the weight of the aircraft in this regard. So it is a very important notion as well that you have to understand very well before you can be able to study further course. And some other notions include the center of rigidity. Here it's a little bit more complex notion. We're going to study this a little bit in better details in the course of strength of material. So it is a point, for instance, if we apply in a force on which we're going to have only, for example, axial loadings without, for example, introducing torque or torque moments. So you can see, for example, of this cross-sectional shape, the U channel, it has a point of center of rigidity which is outside the section itself. So if we have, for example, structural elements and we want to add a certain loading onto that element, we have to take into account where this point is located if we don't want to break this element off. For example, this is how it works for this case of a U channel, right? Moment of inertia, obviously, which is a measure of inertia in the translational motions. And it's also a moment of, so it's also a measure of resistance of a cross-sectional area in terms of, for example, bending moments or torque moments. So, for example, if we have a certain shape or center cross-sectional of certain structural elements, and this element, for example, takes moments like bending moments or torque moments, then in this case, the moments of inertia is going to say how much this shape is going to resist rotation, right? Because moment of inertia is again a measure of inertia in terms of rotational movement, just like the mass is a moment, the mass is a measure of inertia in the case of translational moments. So for example, in order to move a certain body which has a mass, you have to apply a force, so this is Newton's second law of motion. And in order to make an object that has a mass, again, churn around a certain axis, then you have to apply a moment. And here, the moment of inertia is the moments that resists the moments of moving the objects, right? So it's a measure of how much it is difficult or it is easy to make a certain body or certain shape, in fact, churn around a certain axis, and that's how it is calculated. Learn, for example, the x-axis around the y-axis, so we have to define an axis of rotation before being able to calculate this moment. And the polar moment of inertia is also, it is basically the same thing, just in polar coordinates. And finally, the body volume, which is a measure of how much space we have inside of a certain shape. And here, in fact, also, there is a process that is called designing, that is called integrating the aircraft systems inside of the fuselage. So mock-up integration, or the, for example, systems integration. It has to do with the volume that is available inside of the structure, inside of the airframe. And so we study how much every system takes, so how much space it requires in order to be fit, in order to fit inside of the airframe. And we have to make sure that there's enough space there. So we have to calculate the volume also all the time, pretty much, when we integrate systems inside of the airframe, because as you know, the outer geometry of the aircraft is, which is called the theoretical contour, is a fixed boundary. So we cannot like fix anything outside of it, because it has to do with the aerodynamic characteristics of the aircraft. So the outer geometry creates like a boundary, and only inside of that boundary we can integrate our systems, payload, fuel, and so on and so on and so on. So this notion is very important, and the more complex the shape inside of the fuselage, the more difficult it is to determine how much volume we have free inside of that. So we can make some approximations about that in certain design stages of the aircraft, and after that it's going to be through an iteration process corrected all the time and so on. So these are basically all of the geometrical features. So again, the area, the volume, the moment of inertia, and like polar moments of inertia and so on. So other sub-definitions are the basic geometric things that we have to be able to determine. And here, now we're going to see the physical and mechanical properties, which are also have to do a little bit with some basic school definitions, and there are some other definitions which are a little bit more advanced that we're going to be studying in the course of strength of materials and some other disciplines as well. So here we have, for instance, the mass, the density, the force, the moments, and the load, strain, strength. These are a little bit more advanced notions that are going to be studied somewhat in more advanced courses. So in this, our introduction to aerospace engineering, we can only see in general what does this mean, because it is also important to understand what other lectures have to do. So mass, for example, is a measure, as has been said before, of the body's inertia. It's resistant to change in position in space in terms of translational motion, in moving the space, in moving the objects in a straight line, right? So the mass is going to say how heavy it is or how difficult it is to make this body move into space to develop a certain acceleration. So according to Newton's second law of motion, the force is equal to the mass multiplied by the acceleration. So if the body has a mass, then you have to apply a certain force that is going to be proportional to that mass in order to have a certain acceleration, in order to make it move in space in a straight line or in a translational fashion. So as written here, it is a measure of body's inertia multiplied by the Earth's gravity acceleration, right? M multiplied by G. So this is what gives us the force of gravity. And it gives the force the body experiences from the gravitational field in aeronautical as an aerospace. Mass is an essential criterion of rationality of the design. And by rationality of the design, we mean how good the design is, or how optimal the design is, how perfect the aircraft is, if you like. So the better the design, the less is going to be its mass. So that's like a golden rule of designing a good structure. It has to be the lightest possible, and it's given that it works, right? So it should work, but also it has to be, it should have the latest or the least possible mass. So that's why it is an essential criterion of the perfections of design. And moving swiftly on, the material density is a measure how heavy the material itself. So it's it says how much mass inside a unit volume, right? So if we take, for example, a unit volume of let's say 1 centimeter cube or 1 millimeter cube, and see how much mass the material has inside of that unit of volume, then this is going to be the density, right? For example, aluminum, water, titanium, iron, lead, and so on. So all of these materials, they have different material densities, and that's in fact also a criterion we use when we choose the structural material from which the aircraft is going to be manufactured. Here Usually, not the density itself is what is important, but it is the density, the ratio of the density to its strength, right? So because every material has a different strength and it also has a different stiffness level, right? So the strength and the stiffness divided by the density is going to say whether the material is good or it is heavy, is too heavy for example, designing an airframe structure that is going to be good in terms of taking the loads and in terms of the mass. Moving on, the force denoted as P, N, or T, and other capital letters is an impact applied to a point of the body, right, or a structure, which has direction and magnitude. So that is a vector magnitude. So it has a point where it is applied, and it has direction, and also it has magnitude. So it has a certain magnitude. So it has a certain number that says whether this force is big or it is small. So force is the cause of the acceleration of the body according to the Newton's second law. So F equal to m multiplied by a. So the mass multiplied by the acceleration gives us the force. So a force is required to move a body from from one state to another state to develop an acceleration. Moving a little bit on, so the load or loading is any external force or impact causing the structure to strain or to deform, right? So the linear load, for example, is load in a unit length, and linear moments is unit length. So the load is basically a force or a moment, right? And it is defined as the cause of deformation, right? So if the structure deforms, or if the structure feels strained, so if the structure is strained, that means there have to be a load. So the load is the origin of deformation, and it's the origin of structural strain, right? And strain itself, deformation, is any change in relative material position of the body particles associated with their movement in space. So for example, if the initial form of a certain object changes when we apply a load, then that means that we have deformation, or we have strain. And the strength is the ability of the structure, part, or assembly to withstand all types of loadings without failure or thus destruction. So this is the main criterion the designer uses to evaluate his or her structural design. So there have to be enough strength and minimum mass. So we have we know at least two basic criterions for that talk about how perfect is our design, right? So it needs to have the minimum mass and also the enough structure, right? So the best possible strength with the minimum mass together, they will talk about how efficient or how perfect the design of the structure process has been. Now some other general definitions of the loading. So static load, dynamic load, depending on whether it changes in time or it is static over time, so it doesn't change over time. And stress, which is a force per unit cross-sectional area. So this is a measure of how loaded the material itself is, or how loaded the part of the structure is. So it says how much force is applied by a single meter square or single millimeter square of the structural elements, right? So it says how much force is applied as to how much materials we have, right? So if we have a lot of material but the force is small, that means that stress is going to be small. If we have a lot of force but the material is little, so for example, a thin structural element, then that means that element is going to be stressed, right? Why? Because it is a force in a single cross-sectional area. It is a force divided by the area, right? Usually applied as usually the unit is Newton per meter square, like Pascal. And Pascal is relatively a tiny stress for most of the materials, like metals and so on. So for example, 1 Newton is like 1/10 of a kilogram per meter square, so it's a very little force. That's why usually in practice we use the megapascals, or 1,000,000 Pascal, which is 1,000,000 newtons per millimeter square, right? Moving a little bit on, stress occurring from tension or compression loading is called normal stress, and ultimate stress is the maximum value of stress the material is able to withstand, and afterwards it is being basically destroyed. So this is the maximum level of stress the material itself can take, right? And under tension loading strength of materials is measured by their ultimate tensile strength, which is called sigma UTS, right? So when we take, for example, a sample of material and we stretch it, so it will eventually tear off at a certain level of stress, a certain level of force applied by millimeter square, right? So, and that the certain level of stress is called the ultimate tensile strength, and it talks about how much strength the material can take, which is very important for when we choose the material for our structure of the aircraft. And stiffness here also, which is I suppose the last notion that we have to discuss here. It is measured by their elastic models, or the Young's models, which is denoted as E, which is denoted as the big E. So it says how stiff the material is. So if strength talks about the ability to withstand loads without destruction, without being without losing the strength, without failure, while the stiffness talks about taking the load without deformation, right? So maintaining the form, maintaining the shape. So if we apply a load and the material is able to withstand its shape, that means it has a large stiffness, which is denoted again by the large E, and it's also measured by the MPa, so how much newtons per millimeter square is applied. It talks about how stiff the material is. So that's also a basic notion here. Some other notions you're going to be studying better in better details in the strength of materials course, which is going to be a little bit in the subsequent years. For now, we can just see this curve, which talks about how much stress is applied as to how much deformation is acquired in some different materials, and also the Hooke's law, which says how the elastic models, how stiff the material is using this law. As you can see, we have two components, basically the stress and the deformation, right? So we apply a certain level of stress, and as a result, we get a certain level of deformation, and the ratio between them is the elastic models, which talks about how stiff the material is. So we're going to see this in better details, and both in our courses in aircraft design, also in the strength of material.